Here we come to A-Level Physics 2001 structure question 1. Here we are talking about rotor. When the rotor is rotating, the man standing inside it will be pinned to the wall. On the right hand side, it shows a force diagram showing the force acting on the man. So there are two forces, Fa and Fb. We are going to name it. Fa is acting upwards, so this is actually the friction between the wall and the man, so it's friction F. Fb is the normal reaction force on the man by the wall. Part 2. So we know that when the rotor is rotating, the man will be pinned to the wall. In that case, that means upward force is equals to downward force. The friction has been balancing the mg. So we would like to know what is the minimum angular speed. That means we would like to find the omega to keep the man pinned against the wall. So we can write down the equation because it's provided that Fa maximum is equals to 0.4 Fb. Fa is equals to 0.4 Fb at maximum. Now, of course, in part 1, we already know Fa is the friction and Fb is the normal reaction. So I would prefer to write it. I do not write Fa. I write F, friction, and Fb is R. Now, so there are two equations governing the balance of force. Firstly, we know that the frictional force has to balance mg. Okay, upward force equals downward force for the man to be pinned to the wall. And also, secondly, the normal reaction force is equals to mr omega squared, because the normal reaction force is there to provide the necessary centripetal force. So now we have three equations here. We're trying to combine the equations. Now, firstly, from the first equation, F equals mg, but F also equals 0.4 R. So we can write down 0.4 R is equals to mg. And then by equation 2, because R is equal to mr omega squared, so we can further elaborate 0.4 times mr omega squared is equals to mg. And now we are going to put in the numbers. 0.4 m is cancelled out on both sides, so it doesn't matter about the m. R is the radius of rotor, as the diameter is 5 meters, so the radius would be 2.5. Omega is what we want to find, and G is 9.81. So solving this equation, we'll get omega (3.13 radian per second). Part 3. If the mass of the man is greater than 70 kg, would the result in A2 increase, decrease, or remain unchanged? By the previous equation, we already see that m can be cancelled out on both sides. Omega, if you make omega as the subject, omega would be equals to G over 0.4 divided by R. And so there is no mass in this equation. So omega is independent of the mass m. So even if the man is greater than 70 kg, the result would be no different, would be the same. So therefore, in the amusement park, practically, no matter you are fat, you are thin, you all stand inside the rotor. When the rotor starts to rotate, everyone inside would be pinned to the wall when the angular speed reach a threshold value. Okay, so everybody, no matter you are fat or thin, you will be pinned to the wall. So it's independent of the mass. Now we have similar things in space station. So we have a space station. It's designed such that astronauts live in the periphery, the perimeter of the space station, 1 km from the center. So how an artificial gravity of 10 Newton per kg can be created? So we can rotate the space station so that the centripetal force at the periphery equals 10 meters per second squared. In order to find the angular speed, we can calculate the angular speed. So Fc, the centripetal force, is equal to mr omega square. Put in the numbers. Now I want the Fc to be 10. And Fc is equals to mg equals mr omega square. So m is cancel out on both sides. 10 would be equals to r. R is 1 km, so 1000 meter omega square. Solving this, omega would be equals to 0.1 radian per second. And this is how artificial gravity of 10 meter per second square can be created. I should correct it. I'm talking about the centripetal acceleration